What's up, my chemistry students? Mrs. Thompson here, and today we're going to go through neutralization notes. We will be talking about something called titration, okay? Before we do that, here's a mean little chemistry joke. I'll let you digest that. Haha, right? All right, so before we begin, there's a lot of vocabulary that has to be learned before we go through titration. And the first thing is, what does neutralization mean? Well, you've probably said this word before, that things can neutralize each other. Well, acids can neutralize a base, and bases can neutralize an acid. How does that happen? Well, the hydrogen in the acid reacts with the hydroxide in the base, and it forms water, which is neutral. So, therefore, neutralization happens. We can say acids destroy bases, and bases destroy acids. In a neutralization reaction, what happens is the acid and base react together to form salt and water. Okay, so in our example here, this is a common example you've seen probably a ton of times, hydrochloric acid reacting with sodium hydroxide. The hydrogen will come in and kick out the sodium, and then the sodium will come and kick out the hydrogen, and what you end up with is HOH, which we know is water, H2O, and sodium chloride. The sodium is now with the chlorine instead. And as that happens, what we have, this acid-base reaction, acid plus base, always makes salt and water. So we know what's a salt. A salt is any compound that contains a cation from a base and the anion from an acid. In this case, that's our neutralization. All right, so then next, the word titration. Well, titration is a method that we use in lab, and that method is used to figure out the unknown concentration of either an acid or a base. So let's say I have an acid sitting out and I don't know what its molarity is. Well, I can use titration to figure that out. Okay. So the one that we do not know the concentration of, it has a certain name. It's called the analyte because we are going to analyze it. All right. And then it's titrated with the titrant. So the titrant is the standard solution. So there's a lot of names here. Titrant is the standard. Why is it called standard? Because it's been standardized by figuring out what its concentration is. We know the concentration of that one. All right, so here's our basic setup for titration, something you may or may not have seen in lab before. All right, this thing right here, this long skinny tube, is called a burette. We read a burette at eye level. That's why you see this picture of an eye right here. It's not just some strange mistake. It's eye level. So you read it at eye level. All right. Inside of the burette, you put the titrant, the thing that we know the concentration of. Okay. And then inside of a flask, an Erlenmeyer flask, we put the analyte, the solution that we do not know the concentration of. Now this can either be the acid or the base as the analyte, or it could be the acid or the base as the titrant, as long as it's the opposite. So if I know the concentration of the acid, then this would be my base down here. Okay. Or vice versa. All right. The other parts of this is the ring stand to hold the burette with a burette clamp. And as I said before, the titrant also has another name. It's called the standard solution. All right. So number 3, the titrant is added to the analyte until it's reached what we call the equivalence point. Okay, the equivalence point has the word equal in it because two things are equal. That's the number of hydrogen ions and the number of hydroxide ions. This is where neutralization takes place, when all of the hydroxide ions cancel out all the hydrogen ions and form water to make it a neutral solution. All right, next, the end point. The end point is the stopping point in the titration, so end point. Now, this happens at the equivalence point, but we need something to signal where this happens. And so we use an indicator to signal that the equivalence point has been reached. And so we have lots of indicators that can do that. Something that has a change in color at a specific pH. And so there's, if we want to do change color somewhere around here. We would pH of 1.5, we would use methyl violet. Thymol blue, it's kind of pink here to yellow. We could use that here, or this change here. Most often, you'll see us use phenolphthalein, and phenolphthalein changes color from colorless to pink somewhere around close to 8. So I'm going to let you see that in this animation here. And so the titrant is being added to the analyte, and they're swirling. And so then the color change happens. It goes from being colorless to pink. So there's the colorless, drops are occurring, swirling is happening, and then we have a pink color. We will be dealing with strong acids versus strong bases when we're performing titration calculations. Now, if you move on in chemistry, you're going to be dealing with some weak acids and weak bases, and when you do that, you have to worry about equilibrium values. We're not concerned with those. We're just going to worry about strong acid versus strong base. Another thing to note is this is a titration curve. This is what it looks like if we were to graph our information of base added versus our pH. So if the acid is in the flask, the pH increases as we add base, and then there's a steep change when we get close to our equivalence point, and then we just keep adding base and it turns more basic. So what we need for our titration, since the equivalence point happens at a pH of 7, is we need an indicator that changes close to a pH of 7. And so the two options here would be something like phenolphthalein or methyl red. They change color at those points. So the end point, the point that they change color, signals our equivalence point. So right there. All right, so here's the calculation portion of this. It's super easy. It's what we've done before when we were dealing with M1V1 equals M2V2. The difference here is the little n. The little n just stands for how many hydrogen ions and hydroxide ions are in each part of the formula. The A stands for acid, so everything on the left is for the acid, so molarity of the acid, volume of the acid, number of H pluses for the acid in the formula of that acid. And then the right side all stands for a base. So for the N, you're going to look at the formula, see how many H pluses for the acid, and for the base, how many OH minuses are in the formula. Super easy. For volume, it can stay in liters if it's in liters, or you can have it in milliliters. It just needs to be the same unit of volume on both sides of the equation. All right, so here's our example. We've got 42.5 milliliters of 1.3 molar potassium hydroxide. We're going to use that to neutralize 50 milliliters of sulfuric acid. We're going to find the molarity of the sulfuric acid. So the first thing I'd like you to do is to write the equation. So we've got KOH and we've got H2SO4. So we've got our acid and our base. KOH is our base because it ends in OH. H2SO4 is our acid. It starts with a hydrogen. Okay. So then we're going to do a double replacement. The hydrogen will react with the hydroxide because we have to form water, right? And then the potassium will react with the sulfate. And so potassium, we have to go back to our periodic table, is in group 1A, it's a +1. Sulfate, I can look at the formula of H2SO4 and tell sulfate must be a 2-. Okay, so it's K2SO4. All right, and then of course we have the hydrogen with the hydroxide. Now it's always going to form a salt, which we just took care of that, and water. So don't try to make weird funky formulas like H3O. That's not what we're looking for. We're looking for H2O. It's got to form water. We can take care of the fact that there aren't enough hydrogens in our left side by balancing the equation. So we'll do that. We'll put 2 in front of here, which takes care of the 2 potassiums. And let's see, a 2 there. So now I have 2 oxygens here for these 2 oxygens there. All right, so then the next part of this is we're going to use this equation. I want you to separate out your givens to givens for the acid and for givens for the base. So for the acid is our H2SO4. We have H2SO4. We have a volume of 50 milliliters. We have a molarity that is unknown. And because I'm looking at the formula and I can see that it's H2SO4, then I know the number of hydrogen ions is 2. If this was H3SO4, this would have been a 3. Okay. Now let's look at the base. OH minus. We are looking at what? KOH. So KOH is our base. The volume of base is 42.5. The molarity of the base is 1.3. The number of hydroxide ions is 1. Okay, so that's because it's just KOH. Had it been KOH parentheses 2, I would say this is a 2. But there's just one OH in the formula. Alright, so then I plug it in. I have the equation. I want to solve for what's left, MA. So let's divide both sides by everything else except for MA. So that's VANA. And so my equation just becomes molarity of the acid is equal to all of this. So I'll plug that in. Okay. For significant figures, we just look at the molarities and the volumes. The number of H pluses and OH minuses, well, that's counting, so that's unlimited, the number of sig figs. And because our volumes are the same unit, those cancel. Okay, and then we just do the math, and we get 0.55 molar. So that is our final answer. I'm not going to do another one of these. We can do some when you get to class. Hopefully this was relatively easy, as we've done equations like this pretty often in here. I will leave you with one more ChemCat joke. This time I'll read it. It's not as strange. Why are dubstep artists so bad at neutralization reactions? They always drop the bass. All right. See you next time.